Hi, this video is about some vocabulary. We've seen that oxygen binds to hemoglobin. Oxygen binds to hemoglobin in 4 different spots, so you get 4 different oxygen molecules on a hemoglobin at any one time. That's oxygen. There's oxygen. There's oxygen. Oxygen is called a ligand, something that binds to a protein or something that binds temporarily to anything is called a ligand. So oxygen binds temporarily to hemoglobin. Oxygen is the ligand. Hemoglobin, you could think of hemoglobin as just the protein, or hemoglobin as the host, or hemoglobin as the central part of this complex that has a ligand. So this complex, this bunch of molecules with things temporarily attached, this is called a complex. Now, ligand are the things that are attached. Now, I've written a word here, allostery. Allos comes from the Greek meaning other. There's a Greek word that means other, and it's allos. So allostery means other factors involved in how the ligand attaches to the protein. Here's what I mean by other factors. The main factors that are involved in how the ligand attaches to the protein are who the ligand is. So in this case, the ligand is oxygen. If the ligand were carbon monoxide, the stickiness of the attachment would be different. Carbon monoxide, in fact, has a higher affinity for hemoglobin. I mean, hemoglobin has a higher affinity for carbon monoxide than for oxygen. So who the ligand is a central factor in how the binding happens, or how sticky it is, or what the affinity is going to be, or how often it happens. That's not an other factor. Also, the concentration of the ligand. If you have a lot of oxygen molecules, then if the oxygen concentration is very high, then you're very likely to have a lot of ligand bound. If the oxygen is very low, then you are very likely to have very little ligand bound. And we saw that in the graph for myoglobin, the binding curve for myoglobin, where PaO2 was on the x-axis, percent saturation was on the y-axis, and myoglobin looked like this. It looks like this because when there's a lot of oxygen, you're very likely to have high saturation. When there's very little oxygen, you're likely to have low saturation. And as you increase the amount of oxygen in the solution or in the blood, as you increase that, any increase done at low oxygen levels results in a very high increase, a very large difference, a very large increase in oxygen saturation, in oxygen binding. However, any increase in oxygen saturation when there's already a lot of oxygen results in almost no increase in percent saturation. We saw that with myoglobin, and that just makes sense because the saturation of myoglobin with oxygen is dependent on collisions. If you have a lot of oxygen, here's myoglobin. If you have a lot of oxygen and a lot of myoglobin that doesn't have any oxygen on it, well, every collision is going to produce a ligand sticking event. So here collisions producing sticking events. So now the myoglobin is saturated with oxygen. But if you have a lot of myoglobins that are already saturated with oxygen, meaning a high percent saturation, like up here, then every collision is very unlikely to produce another sticking event because each myoglobin can only stick to a finite number of oxygen molecules. So you're going to have a lot of useless collisions, meaning not a lot of change in percent saturation. Now, we saw that in the lecture. So those are the 2 factors that are central to the affinity, or how the ligand is going to bind to the protein, or how well the protein is going to bind to the ligand. Any other factor are just that, other factors. All right, so let me explain that a little bit more with some more pictures. Let me do some erasing here. So allostery is all about other factors. So what are some of these other factors? All right. So if you have hemoglobin and you change the shape of hemoglobin, if you change the shape of the hemoglobin molecule because you do a chemical reaction with something else, that is allostery. you have changed the shape of the hemoglobin molecule, and now it doesn't bind to oxygen as well. So it may bind to, let's say, 2 oxygens instead of to 4 oxygens. So this is something that is not related to who the ligand is, not related to the concentration of the ligand, right? That affects how much ligand you can bind, or how well the protein can bind to ligand. That is allostery. You change the shape, and then you change the ligand binding. That's allostery. What's another allostery? Suppose you change the pH. If you change the pH out here, the pH has nothing to do with who the ligand is. H plus is not the ligand. O2 is the ligand. And H plus, the pH, has nothing to do with how much ligand there is. The concentration of O2 isn't related to, or isn't dependent on, the concentration of H plus. The concentration of CO2 is dependent on the concentration of H plus because of the carbonic acid equilibrium, which you worked on in the Marx textbook a few weeks ago in the homework. But concentration of oxygen is not necessarily related to the H plus concentration. So that has nothing to do with pH, meaning if the pH can change the way hemoglobin sticks to oxygen, the way it the strength with which it sticks to oxygen, or the readiness with which it releases the oxygen, then that is allostery. pH can produce an allosteric effect on the hemoglobin oxygen binding. All right. So what else can be allostery? When you change the shape of the hemoglobin molecule because of oxygen molecules, that is also allostery. So let me do some erasing here. So here's hemoglobin. Yeah, hemoglobin has 4 subunits. When you change the shape from one state to another state of quaternary structure, so this is one state, this is another state. One of these states is really good at binding oxygen. The other state is not good at binding oxygen. Instead, it's really good at releasing oxygen. So that is allostery. Now I know what you're thinking. You're thinking, hey, the difference between these states is caused by oxygen binding. When oxygen binds, the state changes, the quaternary structure changes. Yes, that's true. So there is some influence by the concentration of oxygen. So the influences by the concentration of oxygen are not allostery. But in this case, it's not just the concentration of oxygen. If you do something else to hemoglobin, such as add BPG or DPG, you could still change the way the oxygen binds to hemoglobin. So that means this shape change, this quaternary structure change, it does count as allostery, right? So when you bind, so just to review what I just said there, when oxygen binds to hemoglobin, that changes its that can change its quaternary structure a bit. That change causes the oxygen binding to be more efficient. That is allostery. The change of shape that causes the oxygen binding to be more efficient, that is allostery. All right. So allostery is this broad category of effects on proteins, with the result being a change in the way they bind to their ligands. Right. Now, let me make this a little bit more complicated. Right. So the body is complicated, whether it's human or mammalian or reptilian, whatever it is. Cells are complicated, and we need to understand that complexity. So allostery represents this broad category, allostery. Now, within this category, there is a subcategory called cooperativity. Cooperativity is what we observe with the hemoglobin. So in cooperativity, the hemoglobin concept is included. All right. So when let me draw it as the relaxed and the tense states. Okay, the T and the R states. So in this state, oxygen binding is very weak and oxygen comes off very easily. In this state, oxygen binding is very good and oxygen binds very easily. The affinity is strong, all right? So this state changes when oxygen binds. That's one way to change from one state to the other. You bind oxygen on the hemoglobin and you will change to the higher affinity state, all right? The fact that this is done by the ligand is cooperativity, all right? The fact that the shape change and therefore the affinity change is caused by ligand binding. That makes this form of allostery cooperativity. So we humans have defined allostery as these other effects on ligand binding to a protein other than the concentration of the protein and the concentration of the ligand and the identity of the ligand. And one of those other effects is the shape of the protein, whether it's quaternary or tertiary structure. In this case, it's mostly quaternary structure, some tertiary structure. So this shape change is allostery. But you see, the fact that the shape change is initiated or instigated by the binding of the ligand itself, that fact makes this form of allostery a special form, which we call cooperativity. You can find the formal definition for allostery in the Leninger textbook. Just search for the word allostery. You can find the formal definition for cooperativity in the same Leninger textbook. You could also find these guys by just searching on Google. But I just want you to have the difference clear in your mind. Cooperativity is not the same as allostery. Cooperativity is a subset of allostery. Not all allostery events or not all allosteric situations are cooperative situations, but all cooperative situations are allosteric situations. Thank you.